In this video, we're going to take a look at something called infinite limits. So I've got two graphs on the board. Here's the graph of a function f of x with a finite limit. The limit is this finite number L. So here's the notation we use. We say the limit as x approaches a of f of x is L. We've said what that means can be summarized with this arrow notation. As x goes to a, f of x goes to L. And what that arrow notation means is that as x gets close to, but not equal to a, f of x gets close to L. So when this is a number, that arrow is interpreted as the y values are getting close to that. Now, new definition for an infinite limit. Here's a function g of x that has a vertical asymptote as at a. And we said there's definitely a pattern to the y values. They're going up forever and ever and ever. So we could say the limit as x approaches a of g of x equals infinity. But that, I can tell immediately, is a different definition from what we've given before. Because up until now, limits have been required to be numbers, and infinity isn't a number. Now, I can describe what this means using this same arrow notation. As x goes to a, g of x goes to infinity. So you might say, well, that arrow notation is the same. How is this different? It's how we interpret that arrow. As x gets close to but not equal to a, this arrow here does not mean that we're getting close to infinity. You can't get close to infinity. Numbers correspond to specific locations on the number line. Infinity isn't a stopping point on the number line. Infinity is a symbol that tells us don't stop. Okay. So that arrow is telling us that g of x gets arbitrarily big and positive. So it's a different interpretation. It's not getting close to. It's going to infinity means getting arbitrarily big in the positive direction. Now, that's a new definition. If we were just working with the definition of a limit as a finite number, I would have to say here that this limit doesn't exist. From this point on, we've defined now infinite limits. So if you were given this function and asked to evaluate the limit as x approaches a, you would tell me that it's infinity. Don't tell me it doesn't exist unless I say evaluate all of the limits as finite numbers. Sometimes we want to restrict ourselves to just working with finite numbers because maybe the limit represents something that we need to do. The limit is going to be the number of tons of concrete that we need to order. Well, if we need to order infinitely many tons of concrete, that is not possible. So that's not helpful to know that. Then I would want to say, nope, it's impossible. The limit doesn't exist as a finite number. But if I'm just trying to describe the behavior of the graph, this gives me a whole lot more information than saying the limit doesn't exist as a finite number. Okay. So unless it's specified that limit means a finite number, you can now use either the definition of a finite limit or the definition of an infinite limit. And it will always be clear from the context which you're using. If you say the limit is infinity, you are using the definition of an infinite limit. If you say the limit is a finite number, you are using the definition of a finite limit. Now, with infinite limits, I drew a picture here of a function with a vertical asymptote where we were going up on both sides. Let's suppose I've got a function. Let's actually put the asymptote here at -2. And let's say my function looks like so. We'll call this function h of x. So I would say the limit as x approaches -2 of h of x is negative infinity. As soon as I see that symbol, negative infinity, I know I'm using the definition of an infinite limit. And this would simply mean that the y values, they're not getting close to negative infinity. What they're doing is they're getting arbitrarily large and negative. Okay. So the absolute value is getting arbitrarily big, but they're all negative y values as we get closer and closer and closer to -2. And, of course, we can combine this with our notion of one-sided limits. So if I look at the function 1 over x, the reciprocal function, so here I'm going to just recycle the name f of x and let that be 1 over x. Now this function has a vertical asymptote at 0. It also has a horizontal asymptote at a height of 0. We will talk about horizontal asymptotes in a later section. Right now, let's just take a look at this vertical asymptote, which occurs at x equals 0, the y-axis. So I could say the limit as x goes to 0 from the left of 1 over x. And I could either write f of x here using the name of the function, or I can write the formula for the function. Either is fine. As I'm coming in from the left, it's going infinitely far down, we would say this is negative infinity. If I take the limit as x goes to 0 from the right of 1 over x, coming in from the right, we're going infinitely high up, so that would be positive infinity. And just like with numbers, if you write the symbol infinity with no sign in front of it, it's understood to mean a positive infinity. Some books will use infinity to mean plus or minus infinity. I'm not crazy about that. If I write infinity with no sign in front of it, it's understood to be a positive infinity. And then if I tried to take the two-sided limit, so here I didn't put a superscript, so I didn't specify a direction. Here I would simply have to say that does not exist, because infinity and negative infinity are not the same thing. Coming in from the left, my y values are getting arbitrarily big in the negative direction. And coming in from the right, my y values are getting big, arbitrarily big in the positive direction. You'll notice I'm using the word big to just refer to the size or the absolute value of the number and then attaching a sign. So technically, really big negative numbers are less than smaller numbers. I'm going to, just as a sort of informal convention, reserve the words big and small to talking about the absolute value of something. Okay, so a big negative number is less than a small negative number. -8 is less than -2, but I would say this has the bigger absolute value. Okay, so I'll use less than and greater than for my inequalities. When I'm talking absolute value, I'm going to use the words big and small. Okay, so now we've seen with one-sided limits and infinite limits, we can deal with limits that don't exist, two-sided limits that don't exist as finite numbers, but where we can really describe a pattern or some expectations that we have based on the nearby behavior of the graph.